Before we write software to interface our microcontroller with buttons, we need to look at how we can electrically interface our microcontroller with a button. Now, to do this, we're going to look at a simple simulation of a microcontroller pin and see how it interacts with a switch. So here's my simulation of the microcontroller pin. Now, this isn't a perfectly accurate model. It is just a representation of a microcontroller pin. So microcontroller pins don't actually work like this, but this one works very sort of similarly electrically, and it'll allow us to demonstrate some basic concepts that we're looking at here. And the first thing to notice here is that the pin, when it's set up as an input, doesn't read a 1 or a 0 by default. It reads some floating value, in this case, about 1.63 volts. And that's somewhere in between a 1 and a 0. It's not perfectly accurately a 1 or a 0. So it's a state of uncertainty, and we call this floating. Right, so this is a floating input as it is. Now over here we've got my switch. This is the button itself, and I can open it and close it, and this is exactly how a switch or a button works, right? It's just two electrical contacts. When you press the button, it closes those contacts and allows current to flow from one side to the other. So you might think, hey, if I want the button to, if I want to detect when the button is pressed, I can just connect a wire from the switch to 5 volts and to the microcontroller pin, right? Great, let's see how that works, right? So first thing we notice is when the switch is open, when it's not being pressed, we're still floating, right? Because basically it's no different than it was before when the pin was disconnected. There is no electrical path to either 5 volts or ground when the switch is open. When I close the switch, I do get the behavior that I want, in that the current flows through the switch into the microcontroller pin, and it turns it on. So my little LED indicator here in the circuit says, yes, I'm detecting a 1. This is true and on, right? Great. So the problem remains that when the switch is open, I get a floating voltage. I don't know if that's 1 or 0, and depending on the microcontroller, it might read it as either or both, or it could be basically a random number generator I've hooked up here, right? So what we might think we can do then is, when it's open, why don't we just pull this down to ground? Why don't we just pull a wire? Let's add a wire that goes from here down to ground, right? So now I've got a true 0 on my digital pin. It's a very, very low voltage in the microvolts range, which is basically 0. So that's certainly 0. And let's see what happens when I close the switch. I get an error, right? It might be hard for you to see in this window, but I've got an emergency stop condition, and it's telling me matrix error. And the reason why is because I've got a short. I've got a path directly from 5 volts through the switch onto ground, right? So if this were a real circuit rather than a simulation, it would be the battery and power supply would be heating up, things might catch fire, I might have a lot of really bad things happening, right? So we're gonna stop the simulation, whoops, open that up, we stop the simulation, and everything goes back to normal. So this is part of the behavior. So now we're a little stuck, right? Because I got the behavior that I want for ground, but I lost the behavior I want for 5 volts. So what we really need is something to limit the amount of current that flows in between the when the switch is closed, that limits the amount of current that flows in between 5 volts and ground. So we know what that is. That's a resistor, and that's a really simple little thing to just drop into my circuit here. So I added my resistor, I'm gonna hook it up, and now I get the best of both worlds, right? So now when the switch is open, I'm still pulling it to ground, right? So I get a very low voltage on the pin that detects a strong 0. That's very clearly a 0. And then when I close the switch, I get 5 volts on the pin, a very strong 1, and my LED turns on. I'm detecting very clearly a 1 on this digital input, right? So this resistor is called a pull-down resistor. It pulls the pin down to ground when it needs to, and when the switch is closed, it restricts the flow of current, right? There's another configuration that we can do that uses a pull-up resistor. In this configuration, a pull-down configuration, this is what's called an active high configuration. So when the switch is open, when it's inactive, we read a 0. When it's active, when the switch is closed, when I'm pressing it, when the action is happening, I read a 1. So this is an active high configuration. Now let's look at a different configuration. So this is a active low configuration using a pull-up resistor. So here the resistor is pulling the pin up to 5 volts. So it's pulling it high, it's always high, and then always high when the switch is open. And then when I close the switch, I'm pulling the circuit, I'm pulling it to ground with the switch, and it goes that way. So now when the switch is active, when the switch is being pressed, we're detecting a low level. So this is called an active low configuration of my button. This is an active low button. And you might find there's strengths and weaknesses to either one of these configurations, whether basically we're looking for the lowest power consumption. So depending if it's a circuit that's normally open or if it's normally closed, you might want to use an active low or active high configuration, mainly because you want to minimize the amount of current that flows through this resistor. So this resistor should be placed in whatever configuration that minimizes the amount of current that's flowing through it at any given moment, right? Also, this resistor should be basically a pretty high value. We're talking multiple kilo ohms. I've only got 1K here because that was just what it plopped down by default, but people use 10K resistors very commonly. Again, it's to limit the amount of current. You want a large resistor. A smaller resistor is going to interact with the port itself, and it won't give you as clean of a 1 or a 0 in these configurations. So pull-up and pull-down resistors should always be very large, in the tens of thousands of ohms, rather than hundreds of ohms or something like that. Also, these pull-ups and pull-downs are not necessary for basically anything but switches and buttons. Most other digital sensors are semiconductor based. They have some logic built into them, and they'll drive themselves to high or low. You don't have to put a pull in, a pull up, or a pull down into them. One that comes to mind is it's called a Hall effect sensor. It detects magnetic fields, and that one has, the sensor itself has power and ground, and then the output on it, and that output is driven by the sensor, so you don't need a pull up or a pull down. It's only switches that really need this kind of configuration.